So as I mentioned earlier, I'm going to be talking about applications of graph clustering to certain types of financial problems. So as you mentioned, it will be a mixture of methodology and applications. So I'll try to marry the two, and I might skip some of the slides given the time constraints. So just to recap, the graph clustering problem can be set up as following. We usually have an undirected graph G with n vertices, and where each edge has associated a positive weight, maybe encoding some type of similarity measure between the vertices, potentially as a consequence of using a certain type of kernel, encoding some similarity between the endpoints. And the goal is we want to partition the node set into clusters such that the intra-cluster edges have very high weight, and then the intra-cluster edges have very low weight. And this problem has seen tons of applications in many areas in stats, computer science, biology, and so on. So one fundamental concept I want to highlight at the beginning that we'll use throughout the talk in both the signed and directed setting is that of a graph cut. So typically, if you partition the graph into two subgraphs A and B, the cut between A and B will just be given by the sum of the weights for the edges spanning A and B, okay? And it's a fundamental concept in graph clustering, as you'll see. And the goal usually is partition G into two subsets A and B such that we minimize the cut, right? We put as few edges as possible in the cut, okay? Now, in the last 2 decades, spectral clustering has arguably been the go-to tool for clustering graphs. So in a nutshell, the idea is that you first embed your node points into RK using typically eigenvectors of some type of graph Laplacian matrix, and then you perform clustering by using some standard k-means or k-means plus algorithms. So the motivation for this comes from, about 2 decades ago, Xu and Malik, they introduced an objective function like this one here, where you want to find cluster assignment. So you're minimizing over unknown clusters C1 to Ck. And for each cluster, you want to minimize the cut, except that it's a normalized cut in the sense that you don't want to end up with clusters that have very, very small size. So you divide by the volume of the cut, which is defined to be the sum of the degrees of the nodes in the cluster, right? So the idea is that we want to minimize this quantity. It's an NP-hard problem, unfortunately, like many optimization problems that we care about. But people typically relax this by dropping the discreteness constraints and then computing the solution given by the smallest k eigenvectors to some type of normalized Laplacian matrix. So typically D is a diagonal matrix with the degrees on the diagonal, and L is this Laplacian matrix defined as D minus A, where A is the adjacency matrix of the graph, right? So this has been the standard spectral clustering setup. When you're computing eigenvectors of this Laplacian, we get an embedding, a low-dimensional embedding of our endpoints in RK, and then you use your favorite clustering technique, okay? Now, in recent years, I've started being interested more and more about two families of graphs that I think have been relatively less unexplored compared to their unsigned and undirected counterparts. So these are signed graphs and directed graphs. So there are many applications that involves graphs where the edge weights can take either negative or positive values as well. So the negative values can come maybe from encoding some sort of dissimilarity information. So in social networks, we have friends and enemies, but really the way I arrived at this problem is more through time series clustering. So right, I used to work in finance some time ago, and I'm looking at streams of daily returns for a universe of stocks. And one of the goals there is we want to find clusters of this time series, right? So a reasonable thing that you might do is you want to find clusters such that the blue edges, the negative edges, they are all in the cut because negative edges, they encode dissimilarity. So that's where they should end up being placed. And then the positive edges, the red ones, they should end up inside the clusters because that's where they belong. They encode the measure of similarity, right? So another motivation for this comes from statistical arbitrage. So some of you may know statistical arbitrage typically involves a very large number of financial instruments, hundreds or potentially thousands. But the main idea is that certain quantities are historically correlated, and occasionally, because of whatever market conditions, these correlations are temporarily undone. And then one expects that this previous correlation will be restored in the future. So this SARP can be seen as some sort of a more modern precursor of the good old pairs trading. But the idea here is understand the correlation structure. So can we identify clusters of instruments that are extremely correlated? So this is the task that we're going to be solving here. So a small version of this problem, the most simplest case that you can consider is that of a two clusters, so k equal to 2. So the setup is as follows. You have group elements plus minus 1. Think of them as labels, plus minus ones, the nodes of the graph that we try to uncover. These are unknown. And then the edges encode a measure of similarity between the endpoints. So right, so in the noiseless setting, an edge is just a product of the endpoints, right? So if two endpoints are both +1 or both -1, then the edge similarity should be +1 because they have the same sign, right? And -1 otherwise. But of course, in real life, there's a lot of noise in the data. So somebody comes and flips some of the measurements on the edges, right? And the goal is, given the graph that you see with the edge measurements, can we recover the group elements sitting at the nodes of the graph? So can we recover the label, the +-1? So think of this as just a two community problem. Okay, so in a very simple setting, you can solve this problem by maximizing the following quadratic form. So if A is the adjacency matrix of the graph that has +-1s and zeros if the edge is missing, then if you want to maximize this intra-cluster happiness, then if you think a bit about this, that's one objective function that you can write. So you want to maximize over all x sub i's, living in z to the n. And this quantity is like a +1 whenever you have an edge assignment, a node assignment that makes the edge happy, right? So, okay. And then this problem, unfortunately, is an NP-hard problem because of the integer constraints for the xi. And typically, people do a relaxation by removing the the unit magnitude constraints on each individual xi and replacing it with this constraint that the sum of the squares should be n. But this problem, we all know how to solve. It's just a quadratic form subject to a norm constraint. And then this can be simply solved by the normalized top eigenvector of the adjacency matrix A. Okay, so and yet another way to derive and kind of a motivation for where does the signed graph Laplacian arise from, you can think in terms of maximizing happiness. You want to minimize unhappiness for the edge. Yeah? So Aij is given. And if we find an assignment xi and xj such that this quantity is 0, then the edge is happy. Otherwise, it's unhappy. So if you minimize this objective function and you do a little bit of the algebra here, then you arrive at minimizing this quadratic form, x transpose d bar minus a times x, where this quantity here, d bar minus a, is something that's called the signed graph Laplacian, where it's the usual graph Laplacian, except that d bar has on the diagonal the sum of the absolute values of the entries in A. Okay, so there's been some literature on the signed clustering problem that I'm mentioning here. I won't go into detail, but the idea is that people have used either the signed Laplacian or some various normalized versions of the signed Laplacian for the purpose of obtaining a low-dimensional embedding of the node points, and then they recover the clusters from this low-dimensional embedding. But as you'll see in later experiments, this is not, we can do better than this. Okay, so what we proposed in the recent line of work is that we said, okay, let's take our adjacency matrix A. So let's say we're looking at the whole graph G. We're decomposing our graph G into two submatrices, G plus and G minus, right? So the adjacency matrix of G plus is just A plus. The adjacency matrix of G minus is just it's A minus. And keeping in mind the optimization problem we've seen before, we want to minimize two measures of badness. So if we look for a given cluster C and the complement of C, if we look at the cut, so basically the number of positive edges that live in the cut, potentially normalized by the volume, this quantity we want to minimize, right? Because positive edges, they should not lie in the cut. That's not where they belong to. On the other hand, if we do the same thing for the negative subedges, then this quantity we want to maximize because negative edges should live in the cut. That's where they belong to, okay? So long story short, if you combine these two measures of badness that we want to minimize here, it may seem ad hoc at first by just taking the denominators with some trade-off parameter and then doing the same thing for the numerators with some other trade-off parameter, then we end up with a minimization problem that looks like this. Okay, and I won't dwell on it too much, but you can extend this from two clusters to multiple clusters, but the idea being the same. And this type of objective function here in 11 is what we would essentially arrive by basically replacing these quantities here that denote the cut and the volume. We can always express them in terms of quadratic forms involving L plus. So this is the Laplacian matrix corresponding to the positive subgraph. L minus is the Laplacian matrix corresponding to the negative subgraph. And then similarly for D plus and D minus. So these types of cuts and volumes, we can write them in terms of quadratic forms, which we know how to handle, and we can work towards what's called the spectral relaxation. So I won't go into all the derivations in detail, but long story short, the relaxation to the problem I just described earlier is just given by the bottom equation here, which essentially says that to get a relaxation to this problem, we ought to be looking at the eigenvectors corresponding to the k smallest eigenvalues of this very ugly looking matrix here T, that is the function of L plus, L minus, and D plus and D minus. Okay, so just as a reminder about what's a generalized eigenvalue problem. So for given two matrices A and B, this X is a generalized eigenvector and lambda is a generalized eigenvalue if AX equals to lambda BX. So with this in mind, the algorithm that we proposed, it's embarrassingly simple, and the name is SPONGE and stands for signed positive or negative generalized eigenvalue problem. So you give me a graph G, I split it into two subgraphs, G plus and G minus, and I want to find the smallest k generalized eigenvectors of this matrix pencil here. So L plus shifted by a constant times D minus, and then L minus shifted by a constant times D plus, for some suitably chosen parameters tau plus and tau minus, and then we cluster the resulting embedding of the vertices in RK using k means plus plus. And in the spirit of previous methods, we can also do the same thing for different types of signed Laplacian. So in terms of symmetrized versions of it or random walk Laplacians, just like we've seen in the unsigned case. And okay, so before I show you the some experiments on real data, I should also mention that we could also analyze this algorithm on a signed stochastic block model. So those of you who've seen stochastic block models before might think of this as a natural extension to the signed setting. So we have an Erdős-Rényi graph G on n nodes, and P is the probability that each edge exists independently. And then for each edge in the same cluster, we sign a +1 because nodes are in the same cluster, they are similar, that we have a +1. If they're in different cluster, then the edge weight should be -1. And then we have a parameter eta that independently tosses a coin for every edge, and it independently flips the sign. So that's our noise model. Yeah, so you can write a probabilistic mixture model for this setting that looks something like this. So if two nodes lie in the same cluster, then with probability 0, the edges, with probability 1 minus p, the edge is missing. With probability p is present, and with probability eta, it's a noisy edge. It's a -1. With probability 1 minus eta, it's a correct edge. And you can do something similar when I and j lie in different clusters. And under this SBM model, we could give performance guarantees for the SPONGE algorithm when k equal to 2 and later extend it to higher k. So in practice, if you were to simulate matrices from this stochastic block model, they would look something like this, right? So if eta is 0, if you don't have any noise in the problem, then on the block diagonal, you only have +1s. Outside, you have -1s, and you don't have any edge missing whatsoever, right? So if you start adding noise, so here all this plot I'm showing you have p equal to 1, so all the edges are present, no edge missing. Right, so we have 4 clusters. So here we add 20% noise, and here we add 40% noise. So as you expect, the more noise you add, the harder it is to distinguish the underlying cluster structure, right? So there's some experiments that I want to show here in terms of how do these different methods work when you compare them on this SSBM models. So here we have an experiment with 5 clusters. The edge density in the graph is kept very small, and then on the x-axis I vary the sign flip probability, so the noise level. And the y-axis is the recovery score. It's called the adjusted rand index. So the higher, the better. And you can see that when k is very large and p is not even so sparse, then some methods completely break down. So the one that we're proposing are SPONGE and SPONGE sim, and all the others are existing state-of-the-art methods. And you see already that SPONGE sim does quite a bit better. So it's able to recover clusters at higher levels of noise. And the situation is even more dramatic if you make the problem harder. So we, let's say we set the noise level to 10%, we have 50 clusters, and then the edge probability varies from close to 0 to 0.1. And you see that for very, very sparse graphs, none of the existing methods are able to recover the cluster structure. They basically fail, right? And so one application is to financial time series clustering that we looked here was we took the empirical correlation matrix of 1500 time series. So these are the stocks in the S&P 1500 index. And we computed the bottom k eigenvector of the signed Laplacian matrix L bar. And then we run a standard ML clustering called k means plus plus to recover the k clusters. So if you were to reorganize the correlation matrix sorted by cluster membership, we get something like the picture in the left. Then on the right, we get this alignment with the known sector industries. So I should say that it's not necessarily, the sector industry should be taken with a grain of salt, and they should not really be considered as ground truth. So So, when I very first time I worked in finance some over 10 years ago, one of the projects we were looking at there was try to identify companies that were misclassified with respect to the gig sector. So maybe they could be, labeled as companies belonging to the transportation sector, but if you look at do correlation analysis and you see how they cluster, they tend to cluster more and more the financial sectors, for example. So the way you read the right-hand side here is that the x-axis is the known sectors, and the y-axis, the columns are our so the rows are gig sectors, yeah, this division of the sectors, and the columns are sectors that are clusters that we recovered from our algorithms. And then you can see that one of the clusters we recovered aligns very well with energy and has very little outside of energy. So energy, on the other hand, is also mostly captured by this cluster, but there's some other companies that are not captured well within a single cluster, and they spread over multiple clusters. So if you were to compare our approach with some other techniques like balanced normalized cut, for example, and you ask them to give you 10 or 30 clusters for whatever reason, then they fail in the sense that they give you one very huge cluster. You can see here, and maybe a couple smaller clusters, but then the rest of the clusters are almost trivial in size. While our approach is able to give fairly balanced clusters. Okay, so now let me switch gears and talk a little bit about this problem of directed graph clustering, and then I'll end with some more applications to financial time series. So the motivation here was coming from a financial application of finding anomalies in the network. So now imagine that you have a criminal activity you have a network where some sort of criminal activity is going on, in the sense that workers, let's say in this scheme, they tend to send money higher up in the chain. So the green arrows here are people wiring money higher up in the chain in the hierarchy until the money reaches the leader, and all the other black edges, they indicate financial transactions between the rest of the world and these nodes, or potentially even these criminals. They could be sending money between them just so they confuse the authorities, right? So the challenge here is, how can we tease out the structure? How can we, in some sense, discover these flows of funds in this network? And the problem is much harder. Of course, the problem is easier if you have a clean problem, right? If you just have the rest of the world, this network is very small, and the nodes of interest, they have no other activity. But of course, real data is extremely noisy, and it's not so easy to uncover this subgraph, right? And the challenge here is that the main networks, the rest of the world node is much bigger than the network. It's most of the networks. So then we have to find kind of the needle in the haystack problem. So there's some challenges that arise when we look at directed graphs. So usually, people look at these normalized cut values or other types of similar clustering metrics that are based on edge density. But when you look at directed graphs, these types of cuts often fail to uncover some of the underlying patterns. So the problem here is that these asymmetric relationships, they really contain some sort of some essential structured information about the graph. And then if you do something naive, such as the symmetrization technique, which people have been doing, you lose a lot of the structure. So I want to illustrate this with a simple example. So this data, before we look at the financial example, imagine a network where people migrate from county I to county J in the US. And if you just do a naive symmetrization, M plus M transpose, and you run your favorite standard clustering algorithm on this symmetric matrix, you only end up recovering clusters that align very well with the geopolitical boundaries, which is kind of expected. There's a lot of intrastate migration as opposed to a cross-state migration. But the approach I'll tell you about in a little bit is finding different types of clusters. So we call this Hermitian clustering, and you can see here the clusters recovered. But the gist of the method is the following. We're able to find clusters. So let's suppose here in this Hermitian clustering picture that I'm showing here, we have K clusters. So the idea is that we want to find K clusters such that when we look at the pairwise interactions between the clusters, so they are, K choose two potentially pairwise cluster interactions, all of these cluster interactions, or at least a subset of them, they exhibit a high imbalance. So what do I mean by high imbalance? I mean that when we look at the edge flow between cluster 1 and cluster 2, a large fraction of the edges flow in one direction, let's say from cluster 1 to cluster 2. Let's say 90% of the edges flow from 1 to 2, and only 10% flow in the other direction, right? So one of the top pairs that we uncovered using this Hermitian clustering was this one here, kind of highlighting the fact that a lot of the people are migrating from the green cluster, so like kind of East Coast US, East South, to the North Coast in the US. Okay, and the algorithm is embarrassingly simple. So you give me M, the adjacency matrix of a directed graph. If this graph is not skew symmetric, so meaning you can have edges going both directions for a given pair of nodes, then we find the closest skew symmetric matrix to it by looking at M and transpose. And then we multiply this by the Hermitian imaginary number I. This is a Hermitian matrix. It has real eigenvalues. And then what we could show is that whenever the direction of the edges induce a certain cluster structure in our graph G, then this structure is roughly encoded in the eigenvectors corresponding to the top eigenvalues of this Hermitian matrix A. Okay, so maybe one quick example I'll give here is that let's suppose that the meta graph is just a cycle on 3 nodes, C1, C2, C3. We have this meta graph adjacency matrix describing the flow of edges. So on the diagonal, we're going to put 0.5 because within the cluster, there's no sort of directional content. But across clusters, the way you read this is that from cluster 1 to cluster 2, 25% of the edge, let's say 75% of the mass is flowing from 1 to 2, and only 25% the other way. And then you do something like this for the other pairs, right? And the question is, given directed, we call this a directed stochastic block model generated from this ensemble, can we recover the clusters? And this example is particularly nice because in some sense, you cannot cheat here. So in expectation, for this toy example I've given, all the vertices of the graph, they have the same in and out degree. So you can't like quite cheat and uncover clusters by doing some sort of k-means clustering on features derived from like no degree, for example. So, and of course you can't, the edge density here in the graph, I should clarify, in this graph, right, the edge density here is constant throughout. So you can't also cheat by, dropping directionality and proceeding with some your favorite clustering algorithm, okay? So I'll just make a comment why we think that this approach works so well. So, when people look at symmetrization techniques for directed graphs, well, they typically look at M transpose times M or MM transpose, and this quantity is essentially count the number of common parents or common children for a given pair of nodes UV. While in our case, with a bit of extra work, actually the eigenvectors of this Hermitian matrix A, they don't just count common parents and common children, but also they count, they remove the number of mismatched relationships, so kind of intermediary paths. So like I say here, U points to W and W points to V. So, before I go to the lead-like applications, I just want to show a comparison of this algorithm compared to some of the standard state-of-the-art methods that are based on symmetrization. So these are similar plots to the ones I've shown earlier in the context of this directed stochastic block model. So the higher, the better. And on the y-axis, I varied the noise level. And you can see here already that this Hermitian type kind of clustering approach, they give much higher recovery score than the rest of the methods. And the challenge, the gap in performance between the methods actually is even bigger when you look at more challenging problems. So this is an ensemble with 50 clusters that is very sparse. Only 1% of the edges are existing in the graph, right? But then if you try to recover the clusters, well, at very low levels of noise, basically all the methods give like 10% rand index, while we can get to 60, 70% rand index. Okay, and maybe I won't dwell on this too much, but in the context of this US migration network, as I said earlier, this symmetrization-based techniques, they actually recover clusters that align with state membership, while our Hermitian approach doesn't do so, and is actually giving clusters that exhibit a much higher pairwise imbalance in terms of the flow. Okay, so now let me just skip to the last part that perhaps is the most interesting for many of the people in the audience. So we want to be looking at detecting lead-lag relationships in multivariate time series data. So a lot of the times when you deal with multivariate time series, you have a reason to believe that these quantities exhibit some sort of lead-lag relationships. So for example, what do I mean by that? Well, what I mean is time series A is said to lead time series B if A's past values are more strongly correlated with B's future value than A's future values are with B's past values. So this was a bit of a mouthful, but I'll give a simple example in a little bit. And such lag relationships that often occur in many natural physical systems, economics, biology, even recently in finance, people look at the lag dependence between spot and futures markets, and so on. And there could be many reasons why this lead-lag relationships occur. Maybe literally it happens that one time series has a delayed response to the other time series, or if you keep in mind factor models popular in finance, maybe one time series has a delayed response to a common factor or stimulus that affect both time series. So now we're in the setting that we can leverage machinery from ranking or clustering to denoise these lag relationships. So what do I actually mean by that? So think in terms of this lead-lag relationship are like that, are as follows. We say it can be the case that the return of instrument I on day t may influence the behavior of instrument J on day t plus 3. So we say that I leads J by 3 units of time. So when you build these pairwise comparison matrices, they're going to be very, very noisy and inconsistent. So those of you who've worked on ranking problems this might ring a bell. So it could happen that I leads J by 3 units of time, J leads K by 2 units of time, but I will not lead K by 5 units of time. Maybe it will lead by only 3, or maybe it will lag by 1, just because of how noise fell on this edge measurement. Okay, so we have this lead-lag networks that arise from multivariate time series. There's kind of two approaches we can go about leveraging them. We either compute rankings from these networks and make a prediction in terms of the laggers catching up to the leaders, or we cluster the network and then we infer leading and lagging cluster and we try to leverage them for some sort of prediction task. Okay, so the question is, how do we build a network? So there's many ways to do this. I won't dwell too much on this. I'll just say that there's some simpler ways to do so. For example, your measurement, your matrix Cij, for example, entry Ij is the lag that maximizes the cross correlation. So if the lag is maximized, if the correlation here is maximized at lag 35, entry Ij will be 35. This is not going to be very robust. Something slightly more clever that you can do, you can say, okay, I'm going to look at the area under this curve for the positive lags. I'm going to look at the area under the negative lags. And then depending on which of these two masses is larger, I'm going to direct the edge I to J or J to I. And something else that we've used, and so far it seems to be working the best when looking at the real data, is using the second order signatures. So in a nutshell, this the way you parse this equation here. So I and J are stocks, T is time, let's say current day, and M is your look back window, let's say 60 days worth of data, right? And X is your return. Yeah. So the way, think of this sort of double summation here, is high when a stock by Apple in a certain direction is followed by a move by Google at any later time V. So V is after U, so V is the time. Yeah. Right. So every time Google makes a move in a certain direction, Apple will make a move at that point or later on in the same direction, minus the propensity with which the opposite thing happens, right? So this construction here essentially will give us a lead-lag matrix where entry Ij is a proxy for the propensity of stock I to lead stock J. Okay, so now there's a few things that you can do. So you can, putting your sort of your hat of those of you who've worked on ranking algorithms, you could be tempted to say, okay, I have a directed graph. I can compute a global ranking of the nodes. So in our case of this time series, from most leading to most lagging, so highest rank to lowest rank. And then you have two parameters, alpha and beta, that delimit your leaders and laggers. And then you say, okay, I'm going to use the average return of my top alpha % largest leader as a prediction for the future return tomorrow of the bottom beta % laggers. And this is what I've done some many years ago that kind of started me. So around 2014, I was teaching a data science class at UCLA, and I gave this sort of a mini project to a couple of students to look at a universe of only 10 stocks. So those are the sectors ETFs in the US, and they use some very standard ranking algorithms, so PageRank and CLRank. And they came back to me and they said, right, these are the rankings we found. So there's some consistency across the two rankings. So XLF was first, XLB is second, and so on. So, if somebody asked me at the beginning who's leading in the US market, probably the XLF, the financial sectors, you'd expect would be a reasonable guess. Okay, so then, fast forward a couple of years later, after came a Cucuringu in 2017, I revisited this problem, and I said, okay, let's try to leverage it for some prediction tasks. So I took some macro ETFs, so like SPY, FTSE, Nikkei, IWM, and so on. So, XLF also, VIX, bonds, oil, gold, and so on. So just a very small universe of 10 instruments. And let's see how would this approach here work. So if you look at the P&L resulting from this, the was looking, surprisingly good. So this was 2 ranking methods, off-the-shelf ranking algos that I used to rank networks built from this signature matrix. So the different colors, they denote different execution styles, but potentially with some transaction costs included. But over reasonable amount of data, 3,500 days, this looked fairly promising. Then I did the same thing for S&P 1500, and also looked promising up to some point. So past this is 2003, 2015. So performance was quite weak later on. But one of the things that I did was that I said, okay, let me take the ranking obtained from this network, from the whole S&P 500, and let me compare it with the original data. Right? So remember, you have an input network that you build using your favorite method of choice, signature-based or something else, or correlation-based or whatever. And then you have on the side the denoised matrix that you obtain following your favorite ranking algo. And then you can look at the residual matrix, right? You can look at the difference between these two matrices in absolute value, and then you can cluster it, right? So if you do some type of modularity optimization, for example, on this clustering, on this residual network, if you squint at it from far away, you can kind of see some clusters here. So blue here denotes very low absolute values, so small residual, yeah, and yellow is high residual, right? So this kind of makes you thinking that along the lines that perhaps that it's not so optimal to think that the whole S&P 1500 can be ranked from most leading to most lagging, but more likely we can extract partial rankings along the lines of we first find clusters within the network, and then within each cluster, we can rank from most leading to most lagging in a more efficient way. Okay? And then maybe the third viewpoint, which we took in a very recent paper that I'll try to summarize in the next couple of minutes, was instead of doing ranking, especially since in the meantime I had worked on this directed graph clustering algorithm that are able to tease out imbalanced flows in the graph, we said the following: can we find clusters in the graph such that when I look at a given pair of clusters, you observe a very high imbalance, and then whenever this happens, this could mean that, okay, if you found the relationship between cluster 1 and cluster 2, and 90% of the edges flow from 1 to 2, so stocks in 1 lead stocks in 2, and only 10% the other way around, then perhaps this structure is something that you can leverage for some sort of a prediction task, right? And these clusters here, they need not even be connected to each other. They could be living in the network at different parts of the network, and probably the most of the network is not informative. But at least if you're able to identify pairs of clusters that exhibit strong lead-like structure, then this could be good, right? So together with Josine Reinhardt and Stefanos Bennett, a student here in our department, we revisited this problem in this context, and we used a slightly different data set. So we started with that many NYSE equities from 2000 to 2019, and following some post-processing step, we were left with about 434 equities. And basically what we did, we built this our network using a number of metrics, correlation-based or signature-based. Then we build this metaflow matrix, right? Because after you find clusters, you can compute the cluster-to-cluster flow matrix, right? And then you can also define a metric of leadingness for each cluster, right? So think in terms of the leadingness score of a cluster is the average, or let's say it's the sum or the average of the leadingness value of their nodes. So if you think in terms of just incoming and outgoing edges for lead-lag relationship, it's just looking at the average degree, the average outgoing degree minus average incoming degree of a node within the cluster, right? So this can be a proxy for how much of a leader a cluster is, right? And we did this, and we did a couple of things. I'll only maybe take 3 minutes to explain this, so we at least allow 5 minutes for questions. So we observed a number of things. So we first looked at this is a Jacquard similarity index between our 5 clusters and the usual geek sectors. And there was some overlap, but not much. So mining, so most leading cluster here is 0, and the most lagging one is 9. And our cluster number 1 was a mining cluster, which we know the mining industry is very cohesive. right? And we also did some statistical significance testing based where the test statistics was the largest eigenvalue of the adjacency matrix. And then we also do row and column permutations for the matrices to destroy the structure. And then we're still able to say that, okay, the eigenvalue that we observed from the real data is much, much larger than the eigenvalues we would observe if the data was scrambled and random. And we also observed that these lead-lag relationships are not explained by higher trading volume, because in some literature, people say that higher trading volume are hypothesized to lead lower volume equities, and same thing for larger cap to lead the lower cap ones. So that's not necessarily the case. So for example, here in figure C, we have the clusters from most leading to most lagging, and then this is the average market cap, and we don't really observe a trend here. And the same thing for the if we replace market cap by dollar volume. And then here in A, we actually look at that all flows between all possible clusters, right? So in blue for the GIGS membership, here we used SIC codes. You take the 10 choose 2 edges in your sector to sector flow, and then you compute what the flow there is, what the imbalance is, right? And then we do the same thing for our own clusters, and we actually observe that on average, this distribution of these flows are much higher than you get from the SIC code. So in other words, our data-driven clusters are able to recover higher imbalances that you would observe if your clusters were coming just from your industry SIC codes. And then we also looked at some time variation in the clusterings. So in the sense that we repeated this experiment for every year. So we did clustering for every year in isolation. And then we looked at the adjusted rand index for clusters across time. So we observed here that in the early 2000s, so this is a cluster, this is the adjusted rand index between any pair of clusterings obtained for any pair of years, right? So in the earlier periods, we do observe here higher values. So in other words, the clusterings were more and more persistent in the early years as opposed to they were later on. But I should also say that from the perspective of a predictive signal, it's not necessarily the case that these clusters should live forever, right? As long as you're able to detect such a lead-lag structure, and as long as it persists for some amount of time after you detect it, then this is something exploitable. Because it's not really realistic to expect that these clusters live for like 20-year periods. And then we also put together a small trading strategy that essentially leverages, as I say here, the trading signal is forecasting the lagging cluster return using, so the forward-looking lagging cluster return using some sort of smooth leading cluster returns in the very recent periods. And the P&L plot here looks as you see here, and the Sharpe ratio is 0.62, so not great, but this is indeed a statistically significant signal. So maybe in the interest of time, I'll just maybe I'll stop here, and then if there are any questions, I'm happy to take questions. If not, I'll cover a bit about some potential future works.